In the previous lecture, we have seen the three laws of planetary motion proposed by Kepler. Now, today we are going to derive these three laws. In fact, this derivation of Kepler's planetary laws of motion is based on the concept which we have developed in the previous lectures while discussing the motion of a particle in an attractive central force field obeying the inverse square law. Okay, so let us start to derive first of all the first law of Kepler regarding the planetary motion, which is actually called law of orbit. You have actually studied in the previous lecture that according to Kepler's first law, all planets move in elliptical orbit. In simple way, you can say that the orbit of any planet revolving around the sun is an ellipse. So simply we have to prove here that the orbit or trajectory described by a planet will be an ellipse. And you know, ellipse is such a conic whose eccentricity is less than 1. So in a simple way, we will prove that the trajectory or the conic which will be described by the planet will have an eccentricity less than 1. Here I have shown in this figure that this is just any arbitrary trajectory along which a planet is moving, and we have considered that at the focus of this conic the sun is situated, and at this position P the uh, planet is located. Okay, as you know that the planet moves under the gravitational attraction of the sun, and gravitational force, which is actually attractive in nature, obeys the inverse square law. And in the previous lecture I have discussed in very detail that when a particle moves in an attractive central force field which obeys the inverse square law, what is the general equation of orbit? So definitely if the planet is moving under gravitational force of sun which is attractive and obeys inverse square law, that equation can be utilized. So can you recognize this very equation? That is 1 over r equal to mc by j square times 1 plus aj square cos theta. Can you recognize this equation? You should recognize it because you have studied this equation in the previous lecture when we were discussing actually the motion of a particle in an attractive central force field obeying the inverse square law. In fact, in this problem, there are two bodies. First one is the sun, and another is our planet. Okay, so you can say that this sun, which has, let us consider, mass ms, and the planet which has mass, let us say, mp, this is just a two body problem. And in the previous lecture we have seen that we can reduce the two body problem in a one body problem by taking the concept of reduced mass. So definitely since it is a two body problem because there is an interaction between sun and planet, so we must write the reduced mass of the system in any equation. And if you consider that this small m is the reduced mass of this sun plus planet system, then what is this m? You have definitely you can definitely remember it because I have described it in very detail in the previous lecture. You know that this m will be equal to ms mp divided by ms plus mp, where ms is actually mass of the sun and mp is the mass of the planet. Okay, so in the general equation of particle moving in a central force field which obeys which is attractive and which obeys inverse square law, you should write this reduced mass m of this system at the place of the mass of the particle. Okay. So in this equation you can see I have written that 1 over r equal to mc over j square. Here m is actually the reduced mass of the sun plus planet system times 1 plus aj square cos theta over mc. Here you know this j is angular momentum of the planet, okay, or you can say of this system, okay. J is angular momentum which remains conserved during the motion in central force field. And what is this c? You can say c is actually a constant, and in this case this constant is equal to g times ms into mp, okay. G is universal gravitational constant, and you have seen in the earlier lecture that this constant a is equal to a square root of m square c square j4 plus 2me by j square, okay. I have directly written this equation here because I have already derived this result in the previous lecture, so I have written it here directly. So earlier I have told you that you must watch the previous lecture, previous videos, and then you will understand each and everything more clearly, okay. Now you know that in polar coordinate the general equation of a conic is given like this. This is 1 over r equal to 1 over L times 1 plus E cos theta, okay. This is actually equation of a conic in polar coordinate in general form. Now you can compare these two equations, that is equation 1 and this equation 2. Equation 2 is a standard equation, and equation 1 which we have obtained for a particle moving in a central force field which is attractive and obeys inverse square law. So when we will compare, you can see very easily that at the place of this 1 over L, there is mc by j square. So L, which is a constant, this is equal to j square over mc, okay. And at the place of this eccentricity E in equation 1, there is aj square by mc. So this aj square by mc is actually the eccentricity of the orbit, okay. Now so you can easily say that this equation 1 is same as that of the equation 2, okay. Now we will reduce this equation of conic in polar coordinates in Cartesian coordinate first of all, and then you will see that this equation will change into the standard equation of an ellipse. And for this you can see this figure. Actually in this figure I have considered, as I have told you, that at this position P there is our planet, and at the position at this focus the sun is situated, and if you treat this planet just like a point particle and you consider that x and y are the Cartesian coordinate of this point P, then this let us say this point is S, then this SA will be equal to x and this PA is equal to y. And the polar coordinate of this point, let us say, is r theta. Then you can say this SP is equal to r, and the angle made by SP with this horizontal line, that is you can take it like x-axis. This x with x-axis is theta. So from the geometry of figure you can easily say that this x will be equal to r cos theta and y is equal to r sin theta, okay. So I have written here that x is equal to r cos theta and y equal to r sin theta. This is a very simple algebra. You can square and add these two equations, and after squaring and adding we will simply get x square plus y square equal to r square cos square theta plus sin square theta, but cos square theta plus sin square theta is 1, so that will be simply r square, and therefore you can say r is equal to a square root of x square plus y square. Okay. Now we will substitute this value of r in the general equation of our conic. What is the general equation of conic? You can see this is 1 over r equal to 1 over L times 1 plus e cos theta. And after cross multiplication, this can be written as L equal to r times 1 plus e cos theta. And that will be equal to r plus er cos theta. Now, at the place of this r, we should write a square root of x square plus y square, and this r cos theta is replaced by x. So you can see that L is simply equal to a square root of x square plus y square plus ex. Okay. Now there will be a lot of algebra to reduce this equation in the standard form of equation of ellipse, and let us do it. So you can see, if we take x square plus y square to the power half equal to, then what will be that? That will be L minus ex, and after squaring we will get x square plus y square equal to L minus ex whole square. Okay, and L minus ex whole square, that is simply equal to L square minus 2ELX plus E square x square. Okay. Now take these two terms, 2ELX plus E square x square into LHS, and when you will bring these two terms in LHS, your equation will become x square times 1 minus E square plus 2ELX plus y square, and that equal to L square. Okay. Actually, this is the general equation of our conic in Cartesian coordinate. And this equation will actually represent an ellipse. If the eccentricity will be less than 1, then this equation will represent an ellipse. And for that, we simply multiply this equation, which we have obtained here, which is, I am just underlining. This equation is multiplied both sides by the factor 1 minus E square. Okay. And when you will multiply by this factor 1 minus E square to this equation, what will be your result? You can easily see. This will be, you can see here, in first term this will be 1 minus E square whole square. In second term 1 minus E square will be present. In third term also 1 minus E square, in the RHS also. So you can see your result will be x square times 1 minus E square whole square plus 2ELX times 1 minus E square plus y square times 1 minus E square, and in RHS there will be L square times 1 minus E square, and this will be equal to L square minus L square E square. Okay. Now this term L square minus L square E square is brought in LHS. So after bringing this term in LHS, what will be our result? You can see. The first term, which is x square times 1 minus E square whole square, is written like this, and this is your second term, and L square E square now becomes positive in LHS, and the last term is y square plus y square times 1 minus E square, and that is equal to L square. Okay. Now see the first three terms, which I am just underlining here. You can see this. This is just a square plus b square plus 2ab. This is in the form of a square plus 2ab plus b square. Here at the place of a there is x into 1 minus e square. At the place of b there is le. LE. Okay. So this can be written as x times 1 minus E square plus LE whole square. Are you getting the things or not? This is very simple algebra. Definitely you are understanding. Okay. And the remaining term is y square times 1 minus E square, and that's equal to L square. Okay. Now, this equation can be rearranged like this. You can see when we will take this 1 minus E square whole square as a common factor, then in first term in this square bracket, this 1 minus E square is already present. So this will be x plus LE over 1 minus E square whole square plus y square over 1 minus E square. Okay. Already here there is 1 minus E square, but you have taken the common factor 1 minus E square whole square. So by 1 minus E square, this must be divided. And this is equal to L square. Okay. Now we will again rearrange the terms in the LHS and RHS. When you will divide this equation both sides by L square, your result will be like this. You can rearrange this. See here, this 1 minus E square whole square, when it will be in multiplication, it will be in the numerator. So this equation can be written like this. Now let us put x naught at the place of LE over 1 minus E square and L over 1 minus E square. This is substituted by A. Okay. And L by root over 1 minus E square. This is substituted by B. So this equation can be written like x plus x naught whole square over A square plus y square by B square, and that is equal to 1. What quantities have been substituted? You can see easily here. Actually, we have substituted x naught equal to EL over 1 minus E square. Okay. And A equal to L over 1 minus E square. This is actually the semi-major axis of our ellipse. Okay. Semi-major axis. This is A. Okay. And B is equal to L over root over 1 minus E square. This is semi-minor axis. Okay. So you can see that this equation, that is the equation number 3, actually is the equation of an ellipse. Okay. And you can also see that while deriving this equation number 3, it is supposed that one of the masses is at the center of the coordinate system. Okay. And in the present case, the planet round the sun is at one focus, which is taken as the center of the coordinate system. Okay. So you can see that each planet moves in ellipse with sun at one of its focus. And in this way, you can see that the first law has been proved, according to which each and every planet moves in elliptical orbit. And we have seen that when the planet moves under the gravitational pull of the sun, then it definitely follows an elliptical orbit. Okay. And from these results, you can relate the semi-minor axis and the semi-major axis of the ellipse. And these results will be actually used while we will prove the third law of Kepler, planetary motion. You can see here, since A is equal to L over 1 minus E square and B is equal to L over root over 1 minus E square, so B square will be equal to simply L square by 1 minus E square. But L over 1 minus E square is A, So this can be written as AL, and therefore B will be equal to a square root of AL. Okay, a square root of AL. Okay. So in this way, you can see that we have proved that the orbit of a planet is an ellipse and the sun is situated at one of the focus of the ellipse. Okay. Now we will proceed to derive the second law of Kepler. What is second law? You have seen that second law actually says that when a planet moves, then the radius vector of the planet with respect to the sun sweeps out equal area in equal time. In other words, you can also state this law that the area vector described by the radius vector per second, which is actually called the areal velocity of radius vector, and that is equal to dA by dt. This is equal to constant. This is the second law of planetary motion proposed by Kepler. Now you can very easily prove this second law. Actually, while discussing the properties of central force field, same fact was actually proven earlier. So to prove this second law of Kepler, let us consider this is the elliptical orbit along which a planet is moving, and in course of its motion, let us consider that at any time t, the planet is situated at this point P. I have mentioned that this planet here is at time t. And after a very short interval of time dt, this planet moves to the position P dashed. This dt is very small, very small. And so you can see the figure that in this short interval dt, the radius vector sp, which is actually equal to r, has actually swept out this area which is just shaded here. This is the area swept out by the radius vector in the short interval of time dt. Okay. And we have to prove that this dA by dt will be a constant. Okay. So let us first of all find what will be the area swept out by this radius vector in this short interval of time dt. Okay. So area vector swept out by the planet in time dt. If this is dA, then this will be equal to area of the figure SPP prime times n hat. Actually, I have written here area vector, and you know area vector is always normal to the surface. So the planet, if the planet moves in xy plane, then this n hat will be in z direction. That is, this vector will be k hat. But here I am not considering that the planet is moving in xy plane. So in general, I am taking that this n hat is a unit vector perpendicular to the plane in which this area of SPP dash lies. Okay. Now, as dt is very small, then you can think that if time dt is very small, then this point P dashed will be very close to P. And if P dash is very close to P, definitely you can assume PP dash just as a straight line. So dt is small, that implies PP dash is almost straight. Almost straight. And if it is almost straight, this figure SPP prime will be just a triangle. Therefore, SPP dash, this is a triangle. Okay? This is a triangle. And so, if you want to find the area vector dA, you have to find the area vector of this triangle SPP dashed. And what will be that? That will be 1 by 2 base into height. Base is PP dashed and height will be simply SP or SP dashed. Okay? And you know, since this PP dashed subtends angle d theta at this point S, so from trigonometry you know that this d theta will be equal to PP dashed over R, and therefore PP dashed will be equal to R d theta, and SP is equal to R and times n hat. N hat, you know, is the unit vector normal to this surface. Okay? And so you can see that this area vector is equal to 1 over 2 R square d theta n hat. This is actually the area described by the radius vector in time dt. So what will be the areal velocity of the radius vector? Therefore, radial velocity of the radius vector of the planet with respect to the sun. This is actually defined as dA by dt, you know. Okay? Radial velocity is what? This is dA by dt. And what will be that? That will be 1 over 2 R square d theta dt times n hat. Okay? And this can be written as dA by dt is what? This will be 1 over 2 R square theta dot n hat. Theta dot n hat. Let us say this is equation number 2. Okay. Now, while studying the concept of central force field, you have encountered by this factor R square theta dot several times. Can you remember? Actually, this R square theta dot is nothing. This is simply the angular momentum per unit mass. Because as you know that angular momentum J is given as mr square theta dot. Can you remember it? You must remember. So R square theta dot is what? This is J over M. You know, J is what? J is angular momentum. Okay? Angular momentum. So I have told you that this R square theta dot is simply the angular momentum per unit mass. Okay? So instead of this R square theta dot in this equation 2, you can put J over M. And therefore, this aerial velocity dA by dt is equal to what? This will be j over 2m times n hat. Okay, n hat. Now you have studied that whenever a particle moves in a central force field, its angular momentum remains constant, or in this equation 3 may be written like this. This is dA by dt, and that equal to j by 2m, vector j by 2m. Actually, this j vector will be in the direction of this n hat. Okay, so you can also say that dA by dt equal to j over 2m. Okay, now as we have studied earlier that angular momentum of the particle remains constant while moving in a central force field, and in classical physics mass of the particle also remains constant. Okay, this is actually here reduced mass. So we can say that this dA by dt is equal to constant, and dA by dt equal to constant. What is this? This is, is actually the second law of planetary motion proposed by Kepler, which is called law of area. Okay, so you can see how easily we can prove this Kepler's second law of planetary motion. I think you have definitely understand each and every step clearly, and if you have any problem, you can ask me when this video will be published and it will be streamed. In the comment box you can ask anything. I will be ready to answer your question. Okay, now finally we will derive the third law of planetary motion. So deduction of third law. Deduction of third law. This third law is also called harmonic law or law of period of revolution. Okay, and according to this law, you have seen this law states that t square is proportional to aq. So definitely to prove this law, we will have to calculate the period of revolution of the planet, and when you will calculate the period of revolution of a planet revolving around the sun, then you will see that this t square will be proportional to aq. So now let us consider, according to the first law, that our planet is moving in an elliptical orbit, and let us consider this is our elliptical orbit having the semi-major axis A and semi-minor axis B. We consider it. Okay. Now let us let us consider that our planet starts moving from this point P, and when this planet will move along this ellipse and returns back to this position P, then time taken in this one revolution is actually called period of revolution. Okay, can you say that in one revolution the radius vector of the planet with respect to the sun will describe how much area? Can you say? See here, the planet starts moving from this point P and sun is situated here. So this SP will move like this and describe these areas, and so when one revolution will be completed, the area described by the radius vector will be simply equal to area under this ellipse. Yes or no? Area described by the radius vector when the planet makes a complete revolution will be what? That will be simply equal to area under this ellipse, or you can say area of this ellipse. And with what velocity this radius vector is moving? You know the velocity with which the planet is moving, the radius vector is moving, is called its areal velocity. So just like the linear velocity, time is equal to displacement over what? Displacement over modulus of velocity vector. Similarly, if you want to find the time taken by the radius vector in one complete revolution, you should divide the area described by the radius vector in one revolution divided by modulus of the areal velocity. So you can say period of revolution means time taken by the planet to revolve around the sun once round a trip. So period of revolution T will be equal to what? This is area of the ellipse, and divided by modulus of VA. VA means areal velocity. Okay. And you know that area under this ellipse will be what? This is pi AB. This is just a simple formula for area of ellipse. And modulus of VA, you have seen that this VA vector, which is areal velocity vector, this is vector J by 2m. So its magnitude will be simply J over 2m. And so you can say that this is 2 pi m AB divided by J. Say this is equation number 1. Now, see, we have to relate the period of revolution T with the semi-major axis. But in our equation, there is also the semi-minor axis B. So you must use the relation between A and B so that B may be expressed in terms of A. And you can do it while deriving the first law of planetary motion. We have seen in this equation 4 that B is related to this A by this equation. It means B equal to root over AL. Okay, B equal to root over AL. So if you want to express B in terms of A, you must use that relation. So now you can say that B is equal to root over AL. Okay. Again, when we have written the equation of trajectory, then you have seen the constant L is related to J. See here. L equal to J square over MC. L equal to J square over MC. Okay. So you can replace this L equal to again L equal to J over MC. J over MC. Okay? J over MC. Now, see here. If B is equal to root over AL, then B square will be equal to what? This is equal to AL. And L is equal to what? L is equal to J square by MC. This is J square by MC. J square by MC. Okay? And therefore, B will be what? Again take the square root. This will be J times root over A by MC. A by MC. So you can see I have actually expressed the semi-minor axis B in terms of the semi-major axis A. Now use this result or this equation here in equation 1. It means B will be replaced by J into root over A by MC. Or you can also find that this B by J is equal to what? B by J will be root over A by MC. Root over A by MC. Okay, this is A. Sorry, this is A. A by MC. So now see the equation 1. Here there is B by J. So B by J will be replaced by root over A by MC in this equation number 1. And then we will get the expression for T. So T is equal to 2 pi m A divided by J into there is B. See here, 2 pi m by J, 2 pi m A by J times B, and B is equal to this much. See here, times B, and B is equal to root over A by MC. See here, A by MC. A by MC. Okay. So what will be T square? T square will be 4 pi square m square A cube. 4 pi square m square A cube. Here it will be A square and 1A, that is A cube. And divided by actually something is missing here. J is already eliminated, so you do not write here J, because I have substituted the value of B by J, so J will be not here. J will be not here. Okay. 2 pi ma root over this one. So this is 4 pi square m square A cube and divided by MC. Divided by MC. Okay. Now, sorry, the page has been turned, but this will be just okay. Just 1 minute while left, and the page is turned, but this will be okay. Yes, this is actually MC. Okay, so this M will cancel out, and you can see this T square is equal to 4 pi square M over C times A cube. Now you can see this bracketed term is a constant. Okay, and therefore we can say that this T square is proportional to A cube. And this is actually third law of planetary motion. Okay, this is third law, which is called harmonic law. This is third law of Kepler. So you can see that in a very simple way we can derive all the three laws of Kepler regarding the planetary motion. So in these two videos we have seen that what is Kepler's law, how we can derive it, Now, in the forthcoming lecture, we will see some important applications of these laws, and then we will study some new concept in this central force field problem.